This is VLSI data conversion circuits, lecture 30. In the last class we were wondering how to choose L of S in this particular modulator. Let us say so, the basic idea behind continuous time delta sigma modulation is to make the loop filter in continuous time and sample its output, so that as far as the feedback loop like this is concerned, right, if we break the loop here, the loop would not know the difference between a discrete time loop filter or a continuous time loop filter. For the trivial case of a first order noise transfer function where NTF is 1 minus Z inverse, and assuming for normalization's sake that the sampling rate of the continuous time delta sigma modulator is also 1 hertz, we saw that all that you need to do as far as the loop filter is concerned is to make it an integrator with a transfer function 1 by S. Okay. This way the NTF we calculated to be 1 minus Z inverse, and this is assuming that the pulse shape of the DAC is an NRZ pulse. Now, the process therefore is to try and figure out what L of S one must use, so that if I put in a discrete time impulse here, the sampled output here is giving me the right values. The first sample by definition must give you 0. Is that clear to everybody? Because if it does not give you 0, then there will be a delay free loop which is not acceptable. So, it probably gives you some continuous time waveform like this, whose samples must give you L of Z. So, this is a system with discrete time input and discrete time output, and the impulse response of the cascaded version of the DAC pulse shape and the loop filter after sampling must give you L of Z, which is given by 1 plus, I am sorry, L of Z is computed by the equation NTF of Z is nothing but 1 by 1 plus L of Z. Okay. So, if NTF is known, we know this, and once we know P of t and the discrete time impulse response we need between this point and this point, hopefully we can go and figure out what this L of S is. For the second order example, we said we are going to use a cascade of 2 integrators, and in general if you have a cascade of 2 integrators, the loop filter transfer function is of the form K1 by S plus K2 by S square, and we know the pulse shape. So, we excite this loop filter with a rectangular pulse, in this case an NRZ pulse. Look at the output response. The output response will obviously be a function of K1 and K2, and we go and try and fit K1 and K2 such that the impulse response is what we want. One thing which seems rather surprising is that this is a problem where there are only two unknowns and a lot of equations, correct, and somewhat surprisingly we see that regardless of which two equations you take, the solution you get is always the same, alright. Now, let us try and extend this to a high order NTF.
So, does that mean for any L of Z you can always find an equivalent L of S? Is that what it means? Because you are getting consistent, so let us say that you have infinite number of equations.
Correct.
Let us say that you are not getting consistent solutions if you take any set of, you want two unknowns.
Sure.
You take two equations, you
Correct.
get one solution.
Correct.
You take another set of two equations, suppose if you get another two solutions, right?
Correct.
That means no L of S is possible for a given L of Z.
No, please note that our L of S is somewhat restricted in the sense that we have already assumed the locations of its poles, correct. All we are trying to do is trying to find in more general terms, the denominator polynomial of the loop filter has already been fixed by our choice of two integrators. The only thing we are worrying about now is we are trying to place the zeros of L of S such that it matches the L of Z, right. So, if the solutions do not match for every two any two choices of equations that you choose from this infinite set, all that it means is that this choice of poles is not appropriate, that is all. Okay, is that clear? So, I mean I was hoping to take this up a little later, but since he brought it up, what we are seeing here is that in spite of having an infinite set of equations, in the sense that this sequence here is an infinite sequence all the way from n equal to 0 to n equal to infinity. At first it might seem a little puzzling that even though there are a lot more equations than the variables you need to solve for, namely K1 and K2, taking any two equations is good enough to give you the solution, and the solution is a unique one, right. Whether you take n equal to 1024 and 6752, right, if you take those two equations and solve for K1 and K2, you will get exactly the same solution as you would get for n equal to 1 and n equal to 2, and namely that solution is K1 is 1.5 and K2 is 1, if you want to realize a closed loop noise transfer function of 1 minus z inverse the whole square, correct. I mean at least I would be somewhat puzzled that this is happening, okay. So, please note clearly, I mean the pulse shape does have a bearing on the K1 and K2. The last time around we did see that when we had an impulsive DAC, the K1 and K2 are 1 and 1, whereas if you had an NRZ pulse shape it is 1.5 and 1, okay. You can do the same kind of math for a different pulse shape, namely the return to 0 DAC pulse, and you will find that K2 will remain the same, okay, and we saw the intuition for that the last time around. At low frequencies the noise transfer function goes as omega square, which means the loop filter transfer function must go as 1 over omega square, which means that K2 must go as must be equal to 1, okay. However, K1 keeps varying depending on the DAC pulse shape. If you have a more exotic pulse shape, I mean return to 0 or impulsive or non-return to 0 pulses are not the only pulses in the world, right. A very common pulse shape to have is what the so called exponentially decaying pulse shape. For that, I mean the math will be a little more involved because it's an exponential, but it is still easy to compute. You put, in principle, all you need to do is put the pulse, measure the outputs of the loop filter, express them as functions of k1 and k2 and go and fit k1 and k2 to get the right L of z. No.
Any pulse shape you can find
Yeah.
out corresponding.
Yes, I mean in principle you should be able to find out, for any pulse shape you should be able to find out stuff, and because it is possible to have an infinite number of discrete time systems, I am sorry, it is possible to have an infinite number of loop filters whose samples are the same. For example, if I took a loop filter and translated it in frequency, right, where all, let us say I multiply all the impulse responses by say a number say cos omega t, right. Cos omega t now goes to 1 at 0 and multiples of, I mean at let us say if I multiply it by cos 2 pi 1 hertz times t, this waveform will go to 1 at multiples of 1 second, correct. So if I took an impulse, a continuous time filter, multiplied it with its impulse response by cos 2 pi into 1 hertz into t, while the absolute time waveform is different, the samples of this waveform are the same, correct, which means that if I am able to synthesize a continuous time filter whose impulse response is this L of t that we found here and multiplied it up by cos 2 pi into n times t, where n can be any arbitrary integer, then even though the absolute impulse response will look totally different, the samples of the response will look exactly the same. So this is telling you that it is possible to have any number of continuous time filters whose sampled response is what you want, okay, all right. So in any case, the intuition so far as to choosing the poles of the loop filter has been, oh, in the discrete time domain there are 2 integrators in the loop filter, correct, because at low frequencies you must have 1 by 1 minus z inverse the whole square minus something, okay, that is what L of z is. We say okay, maybe therefore the continuous time loop filter must also have 2 integrators, and then the weights with which you multiply the outputs of these 2 integrators are treated as free variables, and we have solved for k1 and k2, and magically we seem to be getting the same k1 and k2 for whichever set of equations we solve. It turns out that this is not I mean this is not surprising, okay, and the intuition behind that is the following. So let us say we have a loop filter in continuous time with a pole at pk, right. So if a continuous time linear system has a pole at pk, its impulse response must be of the form e to the, so the impulse response is e to the power pk into t, right, and it will be multiplied by some constant which depends on the details of the excitation and and locations of other poles and other such, right. But the key point is to understand that if you have a linear system with a natural frequency or a pole at pk, then its impulse response will contain a term of the form e to the pk times t. Now what we are doing is sampling the output of the loop filter at 1 hertz in our example, correct. So if you sample this e to the power pk times t at 1 hertz, it will correspond to a discrete time sequence which looks like e to the pk times to the power n. Does it make sense? Okay. So what does this say as far as the pole of the discrete time sequence is concerned? Let me refresh your memory and mine too. So if a discrete time sequence a to the power n times u of n is there, what is the z transform of this? Is 1 by 1 minus a z inverse. So this means the pole is at z equal to a. So in other words, a to the power n times u of n corresponds to a sequence, if you think of it as an impulse response of a filter, it corresponds to a filter whose pole is at z equal to a, right. So by the same token, this therefore corresponds to a discrete time system whose pole is at e to the power pk. So a discrete time system with a pole at e to the power pk, all right. So if the pole is at 0 in the continuous time system, what does it correspond to in discrete time? Is 1, and vice versa, right. So if you want to emulate a system with, a discrete time system whose impulse response has components which correspond to zk to the power n, all right, all that you need to do is to find pk using the relation e to the pk is equal to zk. Does it make sense? All right. So now if a system has a pole at therefore if a noise transfer function is of the form 1 minus z inverse whole to the power n by d of z inverse, what can you say about the loop filter poles? Pardon? No, what can we say about the poles of L of z? Okay, so what can you say about the poles of L of z? The loop filter in discrete time has n poles at z equal to 1, which means the continuous time loop filter must have s equal to 0, correct, which means that we will in general you can think of this as which means L of S must be of the form k1 by S plus k2 by S square plus blah 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 kn by S bar n. In other words, you have n poles and the denominator is arbitrary, right. We have assumed that the denominator is arbitrary, I am sorry, the denominator is fixed. We have n poles all at s equal to 0 and the numerator is arbitrary. So, in principle it can vary from, see please note that this is equivalent to k1 s to the power n minus 1 plus kn divided by s bar n. Why have I not said k naught times s bar n in the numerator? So, the only reason for not having k naught s to the power n is because there is, you cannot have a delay free path. Is this clear? I mean, for all practical purposes you can also assume that it is k naught s bar n and find k naught through k n by going through the same process. You have, now you will have how many unknowns in this particular example? You have n unknowns, all you need to do is solve n equations and get the coefficients k1 through kn. And the fact that the continuous time system and the discrete time system are chosen in such a way that e to the pk is equal to zk, that is the relationship between the location of the poles of the continuous time and discrete time system are chosen such that the exponential of the pole of the continuous time system is the pole location of the discrete time system, allows us to without getting into questions of will these k's exist or will are they unique, how do I know that if I solve these any n equations I will get the same values, etc. This should put us put those doubts to rest, okay, because we know that the discrete time system with poles at z1, z2, z3, zn will produce in the impulse response sequences of the form z1 to the power n, z2 to the power n, z n to the power n. Is that clear? And if we choose the continuous time system in such a way that e to the power pk is the same as zk, alright, then the impulse response of the continuous time system will be of the form some constant times e to the power p1 times t plus some other constant times e to the power p2 times t and so on, alright, and these constants of proportionality will depend on the locations of the zeros of the continuous time system, right. However, the samples will be some constant multiplied by e to the power p1 times n plus some other constant times e to the power p2 times n and so on, and by design we have chosen e to the power p1 to be z1, e to the power p2 to be z2 and so on. So, it follows that on this side you have some constants times z1 to the power n plus some other constant times z2 to the power n and so on. On the right hand side you have something which is a linear combination of z1 to the power n, z2 to the power n and so on. So, it is just a matter of matching these coefficients. So, you have n equations in how many ever variables you will always have a unique solution. Is this clear? So, So, given that we understand this, the procedure for finding the k1 through kn is very straightforward. So, what will you do? You have p of t, let me just take an example. This is our generalized loop filter. I can think of this as a chain of integrators all right. You understand? So, can you now tell me how we will find k1 through kn? In general, given the NTF you want to realize, given p of t, okay, find k1 through kn. So, how do you think I will go about doing this? It is understood first that the NTF is of the form 1 minus z inverse whole power n divided by d of z inverse, correct. Only then will all the poles of the continuous time system be at s equal to 0, all right. Now that this is true, what do we do now? Can you tell me a practical way of going about this from scratch? What is the first step? Find L of z from NTF of z equal to 1 by 1 plus L of z, all right. Then what do we do next? Okay, find L of n corresponding to L of z, okay. What next? So, what I will do is notice the following. I am trying to find the sampled output of the impulse response of p of t cascaded with this chain of integrators where the weights of the integrators have been are at this point variables that we need to solve for, correct. So, I can always move the sampling before the summation, correct. So, in other words, I can say this is equivalent to I sample the outputs of this chain of integrators and then form the discrete time sequence, which is the sum of the samples of the outputs of these integrators, correct. So, let me call this L1 of t, L2 of t all the way up to Ln of t. Therefore, the sampled values will be L1 of n, L2 of n all the way up to Ln of n. Is this clear? Now, what should I do? Oh, actually, I'm sorry. Let me just a couple of things which are messy and make this notation bad. Let me do one thing. Let me make this. I'm going to. Okay, so let me see. So, given that the NTF is the form 1 minus z inverse whole to the power m divided by d of z inverse, and given the Dirac-Pult shape P of t, the problem therefore is to find k1 through km, right, such that the continuous time loop filter is indistinguishable from a discrete time loop filter, which gives you the same noise transfer function. Now, how would one go about doing this? First thing would be to find L of z from NTF is 1 by 1 plus L of z, correct. Step 2 is to find L of n corresponding to L of z, right. And now we want to try and find what combinations or what values of k give us the right sampled values, okay. And we can see clearly that the sampling can be moved before the summation and before the weighting of the outputs of the integrators, correct. So, what I am going to do therefore is to move the sampling operation here so this will be L1 of n, I am sorry, L1 of t, this will be L m of t, right. So, this will be L1 of n, this will be L m of n. So, what is this output sequence? What is this output sequence? It is K1 L1 plus K2 L2 and so on plus Km Lm. Is this clear? So, what are we trying to do? You want to make sure that K1 L1 of n plus K2 L2 of n plus Km Lm of n is L of n, right. So, all these are known. Why are they known? We know the pulse shape, and these are nothing but integrals of the pulse shape. Is this clear? So, if L1 through Lm and L itself are expressed as column vectors, correct, then we can write this in matrix notation as L1, I will put an underline there to denote that it is a column vector, correct. You can truncate the column vector wherever you want. I mean, ideally L1 through Lm all run from 0 to infinity. So, let us say you truncate it at your favorite point, okay, which at this time is arbitrary, L1, L2, L3 and so on up to Lm times K1 through Km right equals L, all right. And so, in principle how many equations are there? Let me call this, I am losing out on subscripts here, let us call this P equations, all right, where P is the point at which you have truncated all these impulse responses. So, you need to find m numbers, you have P equations. So, what is the minimum value of P you need? Okay. So, P must be greater than or equal to m, and because of the arguments we made about the choice of the poles of the continuous time loop filter, it follows that if you choose any m equations within in the set P, you will get the same solution. So, clearly if you choose P much greater than m, there are obviously a lot more equations than you have variables, right, but you can actually find a unique solution K1 through Km, okay, and that solution will remain the same irrespective of which set of m equations you choose, all right. I mean, another way of doing this is to say, okay, I am just going to do least squares, and this is A of the form Ax equal to B, I will find the least square solution, but in this particular case it so happens that the least square solution you get will be the same regardless of how many equations there are, which means that this in linear algebra terms, what is this? You are trying to find that linear combination of this vector, I mean of these vectors L1 through Lm, which will give L, all right, and because the poles of the continuous time system have been chosen in an appropriate manner, it will follow that regardless of the number of equations P, in other words regardless of the length of the column vectors L, L1 through Lm and L, the vector on the right hand side, that is L, will always lie in the column space of L1 through Lm, all right. If the poles are not the same, if the poles have not been chosen according to e to the power pk equal to zk, this will not happen, you understand, okay, and you will find that depending on the choice of equations that you use, alright, you will get different values for k1 through km, okay, and then you are now at a loss as to figure out which values of k1 through km to use. Is this clear? Okay. So, anyway, for the time being, let us not worry about it, about that situation. So, if e to the power pk has been chosen to be equal to zk, or pk is chosen to be ln of zk, then you get a unique solution for k1 through km. You understand? All right. So, this is a very straightforward way of doing things. Okay. If of course the pulse is has got some simple form, like it is a combination of rectangular pulses or whatever, then you can even do this with hand, right. I mean, of course, if you have a lot of equations, it gets messy, but it is fairly straightforward. If the pulse is messy, okay, not because you want to deliberately make it messy, because the DAC, the way it is designed, let us say the pulse is not really a rectangle, ideally let us say this is the NRZ pulse that you want. In practice, for instance, no edge can be perfectly sharp. So, a practical NRZ DAC pulse will probably look like this. Okay. Now, it is impractical to go and try and find the waveform and do all this analytically. It is simply easier to generate the DAC pulse, you know, have a cascade of integrators, you pump this pulse through the set of integrators in simulation, right, and in which case these waveforms are known, in which case these will then be known, all right, in which case you can go and determine the case. Is this clear? All right, and that will result in m equations with I mean sorry p equations with only m unknowns, which thankfully can be solved to give you a unique solution. All right.
If
Yeah.
all the poles are not at s equal to 0, and we use instead of 1 by s and 1 by s,
Pardon? Come again?
if all the poles are not at s equal to 0.
No, you start with the discrete time system poles.
Yeah.
So, if you have a discrete time system with poles at zk, you will choose a continuous time system with poles at chosen to be at pk is equal to ln of zk. So, if all the poles in the discrete time system are at z equal to 1, they will all translate to continuous time system poles being at s equal to 0. Now, as we have seen earlier, it is possible to choose an NTF such that the zeros of the noise transfer function are not all sitting at z equal to 1, but are spread in the passband of the or in the spread in the signal band of the noise transfer function, right. I think in third order example you already done something in your homework. Okay. So, that means that on the unit circle the poles are not at z equal to 1, but are, you know, you have some poles which are complex conjugate, they are on the unit circle, but they are not at z equal to 1. By taking the logarithm of those poles, they will correspond to complex conjugate poles in the continuous time system also, okay, which will be close to, if the poles in the NTF, in the discrete time system, are close to z equal to 1, the poles of the continuous time system will be close to z equal to 0. They will not be equal to 0, but they will be complex conjugate and will be close to s equal to 0. So, you need to choose a continuous time system with poles at those particular locations. Is this, does that answer your question? All right. Okay. So, this is a a clean way of finding the coefficients without going through a whole lot of hassle, right. Another popular way of finding the coefficients is to have a dictionary, for example, where you have the equivalent discrete time impulse response. Please note that all we are doing is linearly combining the impulse responses of P of t driving 1 over s, P of t driving 1 over s square, P of t driving 1 over s par n. So, if we sat and computed these responses, right, I mean think of this, each of these systems, the input is a discrete time impulse, the output is a discrete time sequence, correct. So, you can always find the Z transform of that sequence and tabulate your results, correct. So, you say P of t driving 1 over s and sampled at 1 hertz looks like a case in point being an NRZ pulse driving an integrator translates to and sampled zero, 1, etc., which is in the Z domain what? What is the Z transform of the sequence? Z inverse by 1 minus Z inverse. Okay. Okay. So, I make a an entry which says P of t 1 over s in the discrete time domain after sampling corresponds to Z inverse by 1 minus Z inverse. Okay. Similarly, an NRZ pulse driving one by s square gives it is tempting to say it is Z inverse by 1 minus Z inverse the whole square, but it is not quite right, because see you can't take the individual responses and then multiply them. You cascade them in continuous time does not mean that the sampled response is cascaded. So, you have to be a little careful, right. It is I mean admittedly it is quite messy, but this is what people have been doing for a long time. So, I will just do it for completeness sake. So, if an NRZ pulse goes into 1 by s square, what is the how does the output look like? So, the continuous time output looks like this, and after integrating it once more, what do you get? You get a parabola and then you get a straight line. Okay. So, the samples of this animal are this guy, which are 0, half, 3 by 2 and so on. Okay, we continue with this in the next class.